I'll take it.
Alright. Alright, so there's the first round of 5 minutes. Now here's what I'd like for you to do. No, I want you to stop writing. I want you to switch pens. Grab a pen or a marker, something of a different color. Glad to see that that pen is still going around. I had one in like 4th grade. Okay, in the next 5 minutes, you can compare and get formulas from anybody else in the room, including your calculus survival guide. But the reason I want you to do these in a different color, need a different color, is because these are the ones that you obviously didn't remember. These are the ones that you didn't just have instant access to. So if you're thinking about making flashcards, the ones that you're doing in the second color, these are the ones you want to put on an index card because you don't have them on lockdown. 5 minutes, get as many formulas from anybody else as you can. Okay. And adjust as you need to, okay?
I know what you do, I just don't know the formula. It's rectangular, so you have to use your calculator. No, the first arm. That's what we use though.
Sorry about your finger.
The parametric is the one where if you're on the scene, there's two of those that's what I think it is. That's for the portable motion.
This is expensive.
Something like that.
This is dark, this is gray.
Oh, this one's it'll be EXP. This one.
So you don't need Roger. Don't sound crazy.
They're pretty back.
Darkness.
I started watching it with the girls.
It's right there. It's the link at the border curve. Hey, give the R. The link to curve on this border.
Huh? On the part motion of parametric. Oh, I think this one. I got this one. So this is oh no, they're both. Yeah, they're both the same thing. This is just for like the physics concept.
Why would it be beta underneath or instead of like
That's for
or is it parametric?
yeah, these are the same thing. It's just that this one's focused more on like on the physics. This is just in general.
And then they're both BDT.
Yeah,
They are the same.
they're both the same. No, it's arc length.
Do I need to point out something
I
else?
forgot how you put that one, but. And then go.
Do I need to point something else? Yo, no.
What? Integral formulas?
I don't need to review.
Oh.
No, no.
They messing with my intelligence again.
No, don't mess with his intelligence. We know we're jealous of him.
No.
Yeah,
I put beta.
it's not paid up, right?
Oh, I don't remember any of these equations.
You remember?
Volume,
You were there to go to fix
volume, revolution, hollow,
I'm sorry
sorry.
about it.
I
I
forgot
think,
about
I think we need more help on A.
But what's the difference between arc length and
I got these.
Basic.
That's it.
huh?
I got those.
Length
And
and
that's have a
width.
curve like.
Is it the same? Yeah,
an arc
rectangle. Oh, no, he means like in a
What?
rectangular, axis. A
No,
rectangular graph.
Oh, okay.
I'm gonna get my
Look
It
at-
says with.
So,
It says with.
so they might don't
Oh, you're right, you're right, you're right. I was just thinking of it like,
Actual rectangle.
yeah.
And then length of the curve. Lucio,
What happened?
what's the difference between arc length and then the length of a curve?
Arc length and length of a curve, they're both the same.
Yeah.
Okay, never mind.
Do we need to point something?
Someone told me, I'm never mind.
Is this right there? Fine. It's right there.
Yeah, okay.
Do we need to point something else?
Area.
Do you remember the equation?
Yeah,
The
Would
body,
it be
revolution,
interval
solid and hollow. I think back it was just
Oh, no,
like,
this is just like regular area that we were doing before.
Are we supposed to do the back?
Page 17.
Huh?
Are we supposed to do these two?
Oh,
Yeah.
yep.
Does not show.
Oh, I know the end of it.
Volumes of the pollution.
gotta go fast. Well, myself, I just make it the person when
This is 1/2.
Oh, I think. Alright, no, I think that.
how you feel.
Cause
There,
it
here.
depends on the type of shape you
Me.
want.
Cause I remember these, because I was doing right across space, that's it, so.
Like, for cubes, del squared.
B, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q,
Could you do backwards?
C-Y.
Did I put my phone down somewhere? And I know where it is.
Nathan took it.
Thanks for giving me the finger.
C-Y-X.
That's why it was the longest 5 minutes ever.
Why?
I was like, man, I am grading like a fiend back here in these 5 minutes. It may have been a little more than 5 minutes.
20
All right.
minutes.
Formulas. Here they are. Fundamental theorem of calculus, f of b equals f of a plus the integral from a to b of f prime of x dx. Or, right, this is the way that we first learned it when we said final value equals initial plus total change. But this is the way that we actually use it when we're evaluating a definite integral. You find the antiderivative and then you plug in the endpoints. Second fundamental theorem of calculus, that's the one that said that the derivative of the integral of a function, important thing here, a is going to be a constant. Right, this only works if a is a constant. What you wind up getting is f of x. So if I have the derivative of the integral of a function from a constant to a variable, I get the same function back with the new variable. Average value, 1 over b minus a, integral from a to b of f of x dx. The other way we wrote it, we do the integral from a to b of f of x dx, and we divide by b minus a. All right, I bet next two probably went a little bit better. Right, when it comes to area, we're thinking top minus bottom, which is why it was important that I told you that f of x was always greater than or equal to g of x. Area formula, I can tell you from grading the quizzes, we still need to talk about this. I went through, and especially that first part of the free response, we need to talk about, because where you guys still aren't 100% is like what's alpha and what's beta. Figuring out those angles is not our friend right now. All right. Particle motion, if I want displacement, I integrate the velocity from A to B. And if I want the total distance traveled, that's when I'm going to integrate the absolute value of the velocity, also known as speed. Particle motion in parametric mode, if you want total distance traveled, it's going to be this guy over here, which is awfully familiar. It looks a lot like this guy down here in polar, which is not too far removed from this guy over here in rectangular. They're all the same. It's the same formula, again in polar, and parametric, and rectangular, all the same formula again and again. Are you guys okay with these four?
The length of the curve, I didn't know you had to have a 1.
Yeah, so the reason why it has to be this way is that if we're talking about length of a curve, think about all these. In polar, you have an x coordinate, you have a y coordinate, you're taking the derivative with respect to theta. In parametric, you have an x, you have a y, you're taking the derivative with respect to t. Well, in rectangular, don't you have an x and a y? But in rectangular, what are you taking the derivative with respect to? What's the independent variable in rectangular? X. You're taking the derivative of x with respect to x. You're taking the derivative of y with respect to x. And the derivative of x with respect to x is 1. Right? The derivative of y with respect to x is this f prime of x, or dy dx. They're all the exact same formula. And I think it wasn't until like my senior year in college when I was like, oh my god, it's the same thing. Again and again and again and again and again. Why didn't anyone else tell me? I think it's because they didn't know. All right. All right. Now I heard some rumblings about these bad boys here. Okay. If you're dealing with solid, it's going to be pi integral from a to b of f of x squared dx. If you've got a hollow region, right, this would be the kind of problem where you're revolving around the x-axis. Here's some function f of x. Here's some function g of x. X equals a, x equals b. Take this region, spin around the x-axis, and we would ask ourselves the question, is this hollow or is it solid?
Solid.
If I take that region and spin around the x-axis, you guys would all tell me hollow. And so we would, back in the day, we'd say, oh, let me figure out how long the big radius is. The big radius is f of x. Let me figure out how long the small radius is, g of x, and you handle the volume for like the big radius. Then subtract off the volume you get from the small radius and combine it under one integral if you want to. Okay, these next four, this was back in the day, which may have actually even been a full day that we spent on this. Right, we would talk about now you've got some base, some region that is your base. And I'm making my slices are semicircles. And if I've got a semicircle, the constant that you need to know?
Pi over 8.
Pi over 8. If I told you that the slices are parallel to the y-axis, think about those slices.
Yes.
Right, parallel to the y-axis, dx. So it's going to be pi over 8 integral place to place L squared dx. Right isosceles triangle with a leg in the base. The constant. Half. Perpendicular to the y-axis. Perpendicular to the y-axis. My slices go this way. It's a dy kind of slice. The squares, it's just L squared. There's no constant in front. Equilateral triangle. Square root of 3 over 4. Like I want these things to just be, like have them on lock. And then the rectangle, don't fall for it.
Whole square.
You fell for it.
There's no constant.
Don't fall for it.
L times your, whatever your factor.
The problem is, unlike these other shapes, when I say square, you know all four sides are equal. I say right isosceles triangle, legs are equal. If I tell you about the rectangle, it depends on the height. You should always be asking me for like, what's the relationship here? What's the relationship between length and height? Okay. All right. And then the two, I don't know anybody who's really gonna get these. So the only integration we did in the world of series was the integral test. And the integral test, there were three conditions. The function had to be continuous, it had to be decreasing, and it had to be
Negative.
positive. Oh, good! I get them all right, and they're spelled correctly. Yay! And so with the integral test, if you had a series going from 1 to the infinite term, you would find the integral from 1 to infinity and say, does this converge? If this guy converges, so does my series. If this integral diverged, then so does my series. And then we also had a conversation about if you were going to approximate the sum of the series using the first 5 terms, 10 terms, n terms, the way that you get the approximation is you're going to look at what is the integral going to be, and you go from there. All the friends okay? Yes. Good. All right, so that is enough out of me. Now we're going to do challenge by choice. Choice number 1 for the friends in the room. You've got the next 17 minutes. I picked 11 multiple choice questions from the Calculus BC graveyard, going all the way back to 1969. These involve the integration properties that we just went over, as well as some of the newer integration formulas that you haven't played with before. Option 1 is you want to work on your integration skills using these problems. I would recommend that if you're going to do this, you first focus on round 1, which is 1, 2, 5, 6, and 11. These are the ones that are going to be a good review without breaking you. When you're ready for more of a challenge, round 2 is 3, 7, 8, 9, and 10. Crazy Town is number 4. We have never done anything even remotely connected to number 4. I am just curious to see what you can do with number 4 with your smarter paper.
I know.
This is not for a grade. I realize some of you are more energized by this than others. So that is choice number 1. Choice number 2 is folks that want to work with me on the free response question from the quiz. Specifically part A, where you had to find area, and part C, which involved the particle motion, the position vector, all the things. Who are the folks that are going to go over the free response with me?
Well, how do you
Well,
know?
that depends if we got it right.
Okay. fine, be that way. I want my data. Okay, I do not, I'm gonna need all the data back in just a little bit. I do not have grades for you, I just have scores. Nathan. Chepe, you should work on the integration. Chepe, perfect score on the free response. All that time that you've been spending at the spa the last couple of days is time well spent.
Ryan went to the spa.
Alright.
That's pretty good.
You're gonna do the integration practice, right?
Yep.
Good. Alright, so Roger.
I chose D instead. You're right. And I didn't put it there, I'm supposed to flip it.
Ryan.
Data equals 1, so like that was the starting.
Seriously.
Yeah. No, not the same. Yeah, the starting is 1. You're looking from 1 to pilot.
Because I didn't know that.
So this tells me polar is going pretty well, at least on the multiple choice. Parametric, you need to spend a little bit of time studying before you do the testing. Anthony, can I get your data? Alright, okay, so looking at this, I think area is still a little bit of mystery for you in terms of polar. Okay, and Brian. Okay, great. All right, so Lucia, you're doing integration stuff, right? And Chepe, I think you should work on the integration stuff as well.
Yeah.
So why don't the two of you move back here? And Brian, Anthony, Nathan, Victoria, you guys gonna go over polar stuff with me? Can I get the four of you over here then? Yeah, you can keep the quiz. The grade will appear in the grade book this weekend. Okay, but what I wanted to get from you guys right now is the data. Oh, bummer. I was getting really excited for a little bit because I was going to start with something really positive, which is that although the four of you might still be struggling a little bit with area, and that totally makes sense, that you all had the right limits in terms of your angle. And then I read something and I'm like, oh, I'm not as excited as I thought I was going to be because they told you the intersection points. They told you guys the angle. Okay? So, but let's go through this. If they hadn't told you the angle, if the goal was to find the area for the shaded region, what would you do?
Find a point where they equal right here.
You're going to find a point where they're equal to each other. So you're actually going to set them equal to each other. Victoria, what were you going to say? That's what you're going to say. So I need to find the places. So Brian, give me an equation that I could use to figure that out.
3 equals 4 minus 2 sine.
3 equals 4 minus 2 sine theta. Now we're going to stop thinking like calculus students, and we're going to think like pre-calculus students right now, Nathan. What would you do to solve that equation?
Do subtract 1 both sides.
Okay, so -1 equals -2 sine theta. Give me some more. Divide by -2, so sine of theta is equal to 1/2. And I know Mr. S was all about like memorize the unit circle, right? Unfortunately, I think I have lots of evidence that that doesn't actually last. You need to understand the unit circle. So on the unit circle, if I told you the sine of theta was equal to a positive 1/2, which quadrant? Okay, I'd look in quadrant number 1. Here's my angle. The sine is the vertical. And Victoria, we'd also look over here. Great. Well, if this guy over here is a half, what's the angle? Okay, pi over 6 for those of you that speak radians. For me, honestly, I think 30 degrees first, and then it gets switched over to pi over 6. So pi over 6 is the angle that I'm interested in. There's pi over 6. The other angle that I'm interested in, you either use symmetry properties over here, or you use some symmetry, mother, you know the word. That angle's 30, that means that my big angle over here is 150. So theta is 5 pi over 6. Okay? So if they give you the angle measurements, you're good, but I also need you to be able to find them without it. Now, here's the thing. How am I going to find the shaded region?
What I wanted to do is do it from like 5 pi over 6 is and then like all the area underneath where the theta is.
So 5 pi over 6, everything underneath, meaning like
Well, within the circle of the r equals 3.
everything within the circle. Now, so if I start at theta equals 5 pi over 6, and I want to find the area inside the circle, which curve tells me the radius? If I'm going to start here at 5 pi over 6 and move that way, as my pen starts rotating, which curve am I on? Which one is telling me what my radius is? Right? It's the circle. It's the circle that tells me the radius, starting at 5 pi over 6, going all the way until I get over there, kind of making this Pac-Man shape. So a thing that you can do is you can say, oh, well, my area is going to be a half. I'm going to integrate. Now I need my radius. What's my radius? My radius is 3 squared d theta. I need the angle limits of integration. And we need to choose them wisely here. Because if you say go from 5 pi over 6 to pi over 6, we're going to run into a problem. The problem is that 5 pi over 6 is a smaller value than pi over 6. So if you type into your calculator, in fact, if you guys could try this, I'm curious to see what happens. What happens when you do that integral from 5 pi over 6 to pi over 6? Oh, so awkward. And Chepe, as far as I could tell from grading the paper, you were the only one that on part A thought just about area formula for circle.
I was assuming.
And it works beautifully.
So, if I assume, I should assume it's right.
Okay. So if you type in 1/2 integral 3 squared d theta from 5 pi over 6 to pi over 6, what do we get? Negative number. You're getting a negative number. Why are you getting a negative number?
You're going back.
Because you're going backwards. What you guys want to do is go from 5 pi over 6 all the way to pi over 6, but instead you're telling me start at 5 pi over 6 and move this way, move in the clockwise direction. That's what's bringing in the negative. The other thing is you're finding the wrong area. What you would be finding is the area going from here whoop, all the way across, like that windshield wiper kind of action there, right, where you're on the outside curve, not the inside curve. So we've got to we got a couple of options here. A way to fix your limits of integration is say, let me go from 5 pi over 6, that's good, and let me stop here. Why would anybody stop here?
You can multiply by 2.
Right, I can use symmetry and say I'm going from the smaller angle to the bigger angle. That's getting me this area over here. That's a good thing. So 5 pi over 6 to 3 pi over 2, but whatever you're going to get from that, you have to double so that you can talk about that area. are we feeling about this? I mean, this is really like the last area polar conversation we're gonna have. So if there's something that's not clear, now is the time. Sorry, you're good?
Hmm?
Okay, not done. Nathan, why are we not done? Which area?
Four minus two something.
From where to where?
4 minus two something.
Oh, you've got to find, right, basically what we need to find is like that little wedge piece in there. And in order for me to find that area, I've got to figure out which curve is defining the radius, and that's what you said, the 4 minus 2 sine theta. And I'm going to integrate from where to where. I'm going to integrate from pi over 6 from the small to 5 pi over 6 the big. And so your final answer is going to have to say plus this integral pi over 6, 5 pi over 6, 4 minus 2 sine theta squared d theta. What's that equal to? Some number. It's like 24 point something, something, something. Yeah.
If we get like a problem with like let's say there was a small error, like let's say we had one of the intervals wrong, but we also use it for like part B or part C when it comes back, are we still gonna get points off?
No, they will probably be kind and score along with you, but looking at all the polar questions that I've seen, especially when it comes to area, they don't normally build off of that. Right, and I think part of it is just, this is hard stuff. I mean, this is seriously like my 5th year working with students with polar, and I think it is my first time to feel like, oh, I totally finally understand it. So, okay. Anyway, take DC 4 more times, you'll be good. All right, part B, for the most part, everything went well. Part C, I think the issue is we're not reading this question carefully enough. So, we're told in part B, we've got some curve r equals 4 minus 2 sine theta. Okay, not a big deal. And at t seconds, theta is equal to t squared. And you guys did a good job with that. In part C, though, what they want is the position in terms of t. And I think what happened is you guys didn't read this carefully enough. How are we going to find the position vector?
Need the X and the Y variable.
We need x and a y. So how do I find the x and how do I find the y?
X equals R times cosine and beta.
Right, so we need r cosine theta and we need r sine theta. And sadly, although a lot of you all had this, you're not reading that first sentence carefully enough. They are very, very specific about something here. In terms of t, that means t is the only variable you get to
So
use.
could we get rid of this theta and put in t?
Okay, so just like get rid of theta and put in t?
Yeah.
That's going to be a problem.
T squared.
T squared. Because they tell you in part B that theta is equal to t squared. You got me? So now you can't say, oh, r cosine t squared, r sine t squared, because?
Oh, we can say that?
Why can't you say that?
Yeah, the substitute order.
Because what?
You have 2 variables.
You still have 2 variables. They are allowing you 1 variable, and they say in terms of t, 1 variable. So get that r out of there. Right? You can't use r. You're going to have to go back and say, oh, r is 4 minus 2 sine theta. But there's a problem, right? You have to say r equals 4 minus 2 sine t squared times cosine t squared. And then over here, 4 minus 2 sine t squared times, what is this? Cosine t squared. That would be your position vector in terms of t. I've got the x component, I've got the y component, and I've only used t as my variable. They awarded 1 point for the x coordinate, 1 point for the y coordinate. Yeah, Brian.
Isn't that sine? squared.
Cosine and then sine. Thank you. Thank you for that. All right. Are the four of you okay with this?
So we didn't have to actually, so do we have to plug in the actual number?
Okay. You do, but when?
Oh.
The thing that you guys, and Roger did the same thing as well, and we talked about it. They are very specific about what they want. They want the position vector in terms of t. Done, stop. Now, go on to the next part.
So I have to write it there instead of putting T.
Right. Find the velocity vector at time t equals 1.5. So you have to find the derivative at 1.5. You don't ever have to show me the derivative. You just have to find the derivative at t equals 1.5, and your calculator is exceptionally well qualified to do that work for you. That's the thing. Okay? So you went from, it looks like you're going from 0 to pi over 6 using 4 minus 2 sine theta? Yeah. Yes. Okay. So for the 6 of you in the room, and then Roger, wherever the heck he might be. Okay. What I really care about is the test grade. If the test grade is better than the quiz grade will be replaced. You do not need to make corrections, but especially in the world of polar, I think we've just needed a lot of build-up time. Know that whatever happens on this test is the end. All right, see you later. Hey, Jasmine.